Today, now let me try whether we can get into little more complicated proof. If it if it is getting difficult, we will skip it. But just to see a flavor of the proofs in the perfect graphs, and yeah, so as much as I can remember. This, as I told you, the weak perfect graph conjecture was proved by Loas, and a very neat and elegant proof was given for that. What is the weak perfect graph conjecture? It says that chi perfection and alpha perfection comes together, or if a graph is chi perfect, then its complement also is chi perfect, right? So the proof relies on a lemma. We at least try to prove that lemma to see, get a gist of the arguments. So it says that if G is a perfect graph, then you can do a operation called expanding a vertex without losing the perfection of the graph, the perfectness of the graph. So this is the expansion operation. This is G, and then suppose you identify any vertex here, x, any vertex x. Okay. Now you introduce a new vertex x dash, new vertex. And suppose this is the neighbors of x. What should x dash do? X dash should be connected to this. X dash should be connected to this, and also it should be connected to all these things. Okay. I am repeating. So we talk about an operation now by making the graph G a little bigger, means add a new vertex. It's called expanding a vertex. So suppose G is a perfect graph and x is a vertex, any vertex which you can select any vertex, and then you add another vertex x dash, you make it adjacent to x, and then the neighbors are same as that of x, other neighbors are same as x, means whatever was connected to x here will be connected to x dash also. So in the literature we talks about twins. See, for instance, this is a twin of x, as if I've created a twin, right? Because I just copied all the neighbors for that, and I also connected them. This is a true twin. There are two kinds of twins, because you could have made a twin without this. I forgot what we call the other one too. Okay, there is some name for that, but here we are talking about connecting them together. Twins are also adjacent to each other, right? Now, we want to show that if you do it to any vertex of a perfect graph, the resulting graph will again be perfect. So G became G dash now. So G dash is also perfect. Seems to be a simple operation, but is it easy to see? See, for checking that G dash is perfect, you need to check a few things. It is, first, all induced subgraphs are perfect. That means showing the chi equal to omega, and entire graph is also. So, this to take care of this induced subgraph, what we do is we apply induction. In fact, before that you can see what kind of induced subgraphs are here. For instance, an induced subgraph can be here. This can be an induced subgraph, some without x dash is not there at all, suppose taken completely from here. Then we know that G is perfect, and this is a subgraph of G itself. So, it has to obey chi equal to omega, right. For every induced subgraph of G, we had that chi of h is equal to omega of h. So, this will be okay. Even if say this contained x, suppose x was here, still it is okay, because it is again a subgraph of this thing, induced subgraph of G. So, if it had x dash but not x, then still it is fine, but after all x dash is a twin of x, and instead of x I just put x. Structurally there is no change. I know that G was a perfect graph. This is still isomorphic to a induced subgraph of that original perfect graph G. The trouble only comes when both x and x dash belongs to this, right. So, that was not there in the original, right, but still it is smaller as an induced subgraph. So, what we do is to take care of this situation, we just use this induction framework. That means we assume that this statement that a perfect graph retains its perfection when a vertex is expanded like this. For all smaller graphs, we will assume that if instead of G, if I had taken some smaller, means some G dash with less number of vertices, but a perfect graph, and if I had expanded any vertex of that, it will be again perfect. The resulting graph will be again perfect. By an induction framework will be put. Now, I have to do it for G and G dash. Now, any induced subgraph if I take, even if both x and x dash are there, see at least some vertex is outside, right. So, therefore, I can think that a smaller perfect graph was there without, say, this vertex was not there, but then x was there inside that, then I expanded that vertex x in that. So, it is like I got that induced subgraph by expanding the vertex x in a smaller perfect graph, because every induced subgraph of a perfect graph is already perfect. Take an induced subgraph of that perfect graph G, which some vertices are left out from that, and then x is there, but then I expand that x, I got x dash, so it should be perfect. Induction, by induction assumption. So, therefore, we do not have to worry about that aspect of proving this thing for every induced subgraph. That means that comes for free. In two arguments are taking care of that. One is, if the induced subgraph you are talking about contains only one of x or x dash, then because G is perfect, this induced subgraph you are talking about is an induced subgraph of G. If both of them are there and it is an induced subgraph, proper induced subgraph, that means some vertex is missing. That means you can think that it was obtained by expanding this vertex x in a smaller graph than G. So, therefore, by induction, any expansion for smaller perfect graphs will give you only a perfect graph. So, you have to work for only this full graph now, right. This you have to show that chi equal to omega for the full graph, right. This is the only thing you have to do. Agreed. Now, see, the one question we can ask is, I want to show that for G dash, this omega is equal to chi. One question I I know that for G this is true, that omega of G is equal to chi. Suppose when I moved from G to G dash, your omega increased. Omega increased by how much you can increase? By 1, maximum 1, right? If omega increased, then you can easily see that it is suppose this is plus 1, omega to omega G dash plus 1. Then you can easily see that it's an easy case. Why? Because now we can we have also one more color, right? Right. Because you know the chi of G dash also, not x, chi also has increased by 1. Because you only need to be this to be equal, this to be equal. No, this was equal to this increased by 1, and then I can use one more color. So I have one more color. So that what you do is I color it using omega colors here, and this vertex will get a new color. So I hope that is clear, right? So our claim is that if your clique number increased, then that is an easy situation because for omega to increase. So he is asking when can your omega increase? Yeah, omega can increase in only one situation. What is the situation? That x should be part of some maximum clique, right? At least one maximum clique, omega size clique, x should be part of. Then only this x dash contribute to increasing that. That means x dash is connected to all its neighbors. That entire clique will be connected to that x dash, and x dash will also add to that and will be coming. Otherwise, it will never increase. But the point we are making now is if it really had increased by that same way, then it's a very easy situation, namely that because we have only one more color, right? And then that color will simply go to that. Single vertex can be colored that. So we can assume that omega hasn't increased. That means, like he told, this particular vertex is not part of any maximum clique. If at all it's part of some clique, it's all omega minus 1 clique or omega minus 2 clique or something like that. Smaller cliques only it was part of. Not even one maximum clique it was part of. Now what we do is, for the time being we forget this thing. We color G using omega colors. Because it is, this is a perfect graph, omega is equal to chi, and it has the coloring using omega colors. Now you see the color classes. Omega color classes will be there, no? Say the color 1, color 2, color 3, omega colors are there. Now if you concentrate on any maximum clique, the maximum clique has how many vertices? Omega vertices, because it's an omega clique. How many colors will you see on the clique? Only on a maximum clique if you look. You will see omega colors, because the clique should see different colors, and omega clique means omega vertices. Omega colors should come that. That means all colors we have used should appear on the maximum clique. All colors we have used should appear on the maximum clique. But now what I want to do is to remove one color class and destroy all maximum cliques. That means remove one color class and destroy all maximum cliques. But that is quite easy. Any color class if you remove, all maximum clique will be affected. Why? Because the representative of that color class is there in any maximum clique, because the maximum clique, any maximum clique, omega sized maximum clique, no, that all those colors should be appearing on that thing. If I remove the red color, for instance, that red vertex from the clique will go away, so each maximum clique will reduce. If it is not a maximum clique, suppose it's an omega minus 1 clique, then this may not happen because that red vertex may not be there in that clique. But if it's a maximum clique, all the colors have appeared on that. In particular, red color also has appeared on that. If I simply remove the red colored vertices, all maximum clique will reduce. The max clique number will reduce by 1. So now the trick we are going to do here, is that we will reduce a color class, thereby reduce the size of each maximum clique by 1, but still make sure that this vertex is there, x is not removed. That means when I remove the color class, I make sure that x is not removed. So what I do is, I look at the color of x, right? Look at the color of x. Suppose it is red. Suppose it's red in this color. Now I remove the red color class only, but I don't remove x. I remove all red vertices except x. Okay? I remove all red vertices except x. But my claim is that even now, I have reduced all maximum cliques. I have reduced all maximum cliques by 1. Why? Not even one maximum clique remains. Though I did not remove all red vertices, that x I left it there, but still all maximum cliques got reduced. What is the reason for that? X was not a part of any maximum clique. That's what initially told, because x was part of a maximum clique. Then when I added x dash, the maximum clique size would have increased. Right? It would become omega plus 1, and that would have made our life easy. Right? Because we will have only also one more color, and then that x dash would have taken that color. So we know that x is not part of any maximum clique. So therefore, when I remove the red vertices, I can leave x there, because red is the color of x. So I don't need to remove x, right? Because that's harmless, because the remaining red vertex itself is cutting all omega cliques, all maximum cliques. So now x is still here, all other maximum cliques, all maximum cliques have reduced by 1, right? Now if you, so say suppose R is the set of vertices which you removed, R minus x, right? This is what you removed, let's call it R dash. So now you look at G minus R dash, right? The graph after removing these red vertices except x. But its maximum clique size is what now? Omega minus 1, because we have removed at least one vertex from each maximum clique of the original G, right? So now it's omega minus 1. But it is a perfect graph, right? Because it's G's subgraph only. It is G's induced subgraph only. So it's a perfect graph. Therefore, it's a perfect graph. It has only maximum clique size omega minus 1. So it has the chromatic number equal to omega minus 1, because that's a perfect graph, right? Any induced subgraph of a perfect graph is again a perfect graph. So we have an omega minus 1 coloring for G minus R dash. Okay. So we have colored all the vertices of G minus R dash by omega minus 1 colors. Now what I do is, I go back to G by putting back that R dash, but along with that I put my x dash also. X is already there, right? Along with that I can put my x dash also. What is the reason? Because this R dash and x dash, if I put x dash along with R dash, it is still an independent set. Do you notice that? Because including x, that R dash union x was the R, that red colored vertices, because x was also red colored, right? And but I carefully kept x inside. So only R dash, except x, I removed all vertices back. But now when I am putting back, I am putting also the x dash, because x dash is like x only. It will be an independent set. What I am putting back is only an independent set. Now how many colors are required to color this new graph? One more, because that independence that needs only one color. No, that is omega minus 1 plus 1. Omega colors is only required, right? So therefore, we have omega colored this entire thing, right? Isn't it? Assumption was that the clique number was omega, so we colored omega using. It's a little tricky, but have you understood it? So, you haven't removed x. No, there is no clique of size omega. See, the argument is that initially we asked, does when I add x dash to G, will the clique size increase? Will the maximum clique size go up by 1? That can go up by 1 only if x is part of some maximum clique in G, right? So, but if it had gone up, then we have also one more color, because omega became omega plus 1, chi only need to be omega plus 1, one more extra color, but this entire G is colored by omega colors, this except only one vertex is to be colored now, that extra color will be given to that. That single vertex will get that single color. So, that is a very easy situation. Therefore, we can assume that this omega is not increasing, that the clique number is not increasing. But if the clique number is not increasing, that also means that that particular vertex x, which got expanded, was not part of any maximum clique. Because if it was part of even one maximum clique, that clique size would have got bigger, right? So, that is the saving grace. Means that x is luckily not part of any maximum clique. Now, what I did is, I colored this full G with omega colors. It can be done because it is a perfect graph and omega is equal to chi there. And now looked at the color of x, it happened to be red. And now my point is to remove red colored vertices completely, which will decrease the cardinality of each maximum clique by 1. But then my observation is that, okay, you can do that even without removing x. You can remove all red vertices except x, because x has no role. X is not part of any maximum clique. Even if you remove the remaining red vertices, all maximum cliques will go down by 1, because they have to cut, the red vertices should cut all maximum cliques. Anyway, x is not contributing to that cutting maximum clique business, right? So, let it be there. The remaining things will remove. Once I remove it, what happened is all maximum cliques reduced by 1. So, it is an omega minus 1 is the maximum clique cardinality now. Now, that is also a perfect graph. After all, it is the subgraph of G. So, because it is a perfect graph, it has a omega minus 1 coloring also, chi equal to omega minus 1 there. So, use that coloring, change the coloring, and now use that coloring, omega minus 1 coloring. But now I want to go back to the full expanded graph. So, what is to be put back? That red colored vertices except x, because x is already there, and that x dash, but x dash is like x only. I can mix with that this red colored vertices, because that is anyway independent, right? X was a red colored vertice, like a full set of red colored vertices are put back, right? We can give a new color to that full independent set. So, that is why it becomes omega colored now. So, omega clique, omega colored. See, the subtle argument, okay, because I have told it very smoothly, it went into your head. So, evening you try to repeat it in your mind, may not come, right? So, so therefore, what we have proved is the expansion operation retains the perfection. You can take any vertex and expand it, then it will still be perfect. Start with a perfect graph, take a vertex, expand it. It will still be perfect. You can take another vertex, expand it. It will still be perfect. Or take again the original vertex and expand it once again. It will still be perfect. You can do the expansion any number of times, right? So, that is what. Okay. So, this will be, this is one lemma he relies on proving the thing. Now, let us see what you want to prove. So, you want to prove that if the graph G is chi perfect, its complement is also chi perfect, or if the graph G is chi perfect, it is also alpha perfect. Now, to prove this thing, as usual, the difficulty is that we have to worry about all induced subgraphs, right? You go to the complement, we have to show that it is chi perfect, not only the complement, all its induced subgraphs. But that is not a big deal because you can use induction framework, because induction framework kinds of get rid of this all induced subgraph, proper induced subgraph problem, because what you can do is you take G complement and take any induced subgraph of it which is proper, that means strictly smaller than the G complement, and then that is the complement of the corresponding induced subgraph of G. So, if by induction if you assume that for any perfect graph of smaller cardinality, smaller order, it means smaller number of vertices, its complement is perfect, then for induced subgraph it worked already. Agreed? That means what I am telling is to prove that, see, if G is chi perfect, I want to show that G complement is also chi perfect, right? So, I am claiming that you only have to worry about the full G, you do not have to worry about that induced subgraph part, because induced subgraph part comes free by induction framework, because if you take any proper induced subgraph that is smaller and it is actually the complement of the corresponding induced subgraph of G, right, and that is anyway a smaller perfect graph, its complement is known to be, by induction hypothesis, known to be chi perfect, right, chi perfect there, chi perfect in the complement. So, therefore, it is done. So, we only have to prove that full complement has this chi perfection, chi is equal to omega, or in other words the full graph, original graph has alpha perfection, that is alpha is equal to clique cover number. We will go by the chi perfection of the complement. So, we have to show that the clique number is equal to chromatic number. The same question we will ask, is it possible that if a clique cuts all independent sets of the complement, right? Is it possible that a clique cuts all the independent sets of the complement, right? Or in other words, is it possible that some independent set is there which has representative on all cliques in G, right? Is that possible? Right. So, the if you have so what we are saying is that for every okay, if you can look at the independent set, the maximum independent set of the complement probably, right, and then yeah, maximum independent set of the complement you look, we can ask all these questions. So, and if you look at the complement, take the maximum independent set there, and then you ask whether this maximum independent set can intersect with all cliques of the complement, all the full complement. Then what happens is, if I remove that maximum independent set, then what will happen? All maximum cliques in the complement will reduce by 1, right? Reduce by 1. So then, but that is a smaller graph now. You have removed that big one independent set. So now the clique number has gone down by 1 there, right? Isn't it? Now that part, by induction hypothesis, this part is a complement of some smaller perfect graph. So therefore it is also a perfect graph. Now omega minus 1, so whatever clique number was there for that complement, let's say omega dash minus 1 is the clique number there. So omega dash minus 1 coloring is there, but then we can put back this independent set, right? And that requires only one color. So it is omega. So that means this is a trivial case we are considering. So I'll repeat this entire argument once again. So what are we trying to do? We are trying to prove that if G is perfect, chi perfect, its complement is also chi perfect, right? If G is chi perfect, its complement is also chi perfect. So now, as I told you, I don't have to worry about proper induced subgraphs. So I only have to worry about the full G complement, right? Because any proper induced subgraph of G complement is the complement of some proper induced subgraph of G, and because it is a smaller perfect graph, and the by induction hypothesis we know that for smaller perfect graphs, if G is perfect, G complement is perfect. So we are done. So we only have to worry about proving that full G complement is perfect. Full G complement is perfect, chi perfect. So I look at the trivial case. So let's say G complements. G complement has this clique number omega dash or something like that. Its maximum clique size is omega dash. That means I have to demonstrate that I have an omega dash coloring, right, for G complement. Omega dash coloring for G complement. This omega dash may be different from the omega of the original graph. In the complement, omega dash is the clique number. Now, the trivial question to ask is that, or the trivial case to rule out is that, is there any independent set? Is there any independent set in the G complement such that that independent set intersects with all maximum cliques of G complement? That means all omega dash cliques of G complement, it's intersected by some independent set S. Is it possible? I am claiming that obviously it's not possible. Why? Because we are done. We are done? Because in that case you just remove that independent set. When you remove that independent set, we get some proper subgraph of G complement. We know that it's already perfect, right? And by induction hypothesis. Now this perfect graph's clique number is what? Because when you removed this, yes, it was intersecting with all maximum cliques. So therefore it has reduced the cardinality of all maximum cliques. So therefore it has become omega dash minus 1. So that graph, means G complement minus S can be colored using omega dash minus 1 colors because it's a perfect graph. Now put back your S, right? That needs only one color. No, it's an independent set. So how many colors are used? Omega dash colors are used. So therefore it is omega dash colorable, right? So chi perfection is proved there. So what do we infer? If there exists an independent set which intersects all maximum cliques of G complement, we are done. So that means G complement cannot have an independent set which intersects with all maximum cliques of complement. So now let's go back to G. So what does it say? This independent set will become clique, right? In the original. That means in G we cannot have a clique which intersects with all maximum independent sets, right? Because maximum cliques in G complement becomes maximum independent sets in G, right? So going back to G, we are saying that in G there is no clique, not necessarily maximum clique, no clique itself, such that clique K such that K intersection S is equal not empty for all S, right? Means K intersects with all the S independent sets. Like that, we cannot find a clique is what we told. Are you convinced about this? Actually, we have only on the trivial part of the proof, right? We have ruled out the trivial case and we got this. Now, if you don't understand, just ask, because there is no point writing it just down and all, because this is about some tricky argumentation. You have to track the argument well. So, anybody who is confused here? Any questions? Because this is the first part of the proof, which is at least I hope that you understood what we are about to prove. We want to prove that G complement is chi perfect. To prove G complement is chi perfect, you should have proved for all induced subgraphs, but that any proper induced subgraph, it comes by induction hypothesis. We don't have to even worry, right? Because all proper induced subgraphs by induction hypothesis is the complement of a smaller perfect graph, and therefore it is perfect. Now, full G complement, I have to show that chi equal to omega. To show that, one trivial case is being considered. So, that means if I could have found out one color, right, I mean one independent set, right, which I could have removed and reduced the clique number of the complement, then my work is done. Why? Because if I can find one independent set and I remove it and the clique number there reduces, then I got the entire remaining graph can be colored with omega dash minus 1 colors, because 1 less than the clique number of the original G complement, because you manage to reduce the clique number, but it is by induction perfect, right, because smaller graph, right. So, therefore, omega minus 1 coloring exists there, but what we removed was only an independent set. We can put it back with just one color, right. So, omega coloring exists for, omega dash coloring exists for G complement, that is done. So, that is the trivial case. That means it will never happen. That means if you consider any independent set of the complement, G complement, you will never be able to intersect all maximum cliques of G complement with that. So, one clique, even if you remove that full independent set, any independent set, one clique will remain, one maximum clique will remain alive, right. So, the clique number will not reduce. So, this entire idea we took it to G and we talk in G now. So, that instead of saying independent set, we will say clique, and instead of clique, we will say independent set. That means there is no clique in the G such that this clique cuts all maximum independent sets of G. Or in other words, if you take any clique in G, you will be able to find at least one maximum independent set such that this clique does not have any representative in it, does not intersect with it. Agreed? So, I will stop here and ask whether you are okay with it, and then if you are understanding it. Now, this is indeed a tricky proof. There are these kind of arguments are just very logical arguments. That's all, because may not be very easy to catch in the first go, but it's reasonable arguments, no problem. If you concentrate well, you will understand it. The difficult part is the creative part, in the sense that how an idea comes, right. This idea, particular idea which you are going to tell, does not seems to be implied by the problem at all. It does not seems to connect directly to the problem. I mean, why this should be considered is not clear. But up to now, what we are told is very much, I mean, it's a very logical argument in the sense that it comes, if you try it, if you think about it, you will understand it. It's slippery arguments, but perfect. Now, the next thing what we are going to do is a little creative. What we are going to do now is in G, we collect all cliques. All cliques. So, we can write down so I am not saying maximum cliques or something like that. I am just collecting all cliques. I will write them K1, K2, something. Sorry, K, let's say K, H, where H is the number of cliques. It can be a very large number, right? I listed down all the cliques of the G. Now, what I do is, look at K1. I know that there is at least one maximum independent set in G which does not intersect with K1, right? So, I may get more than one, but I get at least one. I take one and I associate that S1 with this thing. I will write it like this. That is an independent set. But this is a maximum independent set, not Si is equal to alpha always. This may be whatever, I do not care. And similarly for K2, I will find one S2 such that S2 will not intersect with K2. And similarly for Ki, I will find the Si, that Si intersection Ki is equal to empty. And finally for Kh, SH, SH intersection Kh is equal to empty. The point is that these things may even repeat, I do not care. Okay, maybe S1 and S2 may be same also. Okay. Now, we will construct a new graph from G, let me call it G dash, by these expansion operations, expanding the vertex operations. What am I going to do? I take a vertex X in G and run through this thing. I will go with that vertex X and ask S1, is this vertex inside S1? Is this vertex inside S2? Is this vertex inside S3, like that? And I count the S answers. How many times I hear S? Yes, I am there. I am okay. This there is there. I mean the in how many SIs particular vertex X is part of. Let's say it's the multiplicity of X in this collection, M of X, right? How many times X appeared in these sets? How many different sets SIs this X appeared? So that's a function I define for each vertex X of G. For each vertex X, I can find out how many times it is, how many of this independent set is part of. Now what I do is, I take a vertex X, I expand it M of X times, right? I expand it M of X times. Suppose M of X was 10, that means if X was in 10 different SIs, right? Here, 10 times I heard yes answers from here, then I expand X 10 times. Okay, 10 times means 2 10 copies. For instance, 1 times means we are not expanding, we are just keeping it as such. 0 times means I am just removing it, right? 0 times means I am just removing it. 2 times means the usual expansion, another copy will come, a twin will come. 3 times means 2 twins will come, a total 3 will be there, X, X dash and X double dash kind of. Is it clear to you? So, in other words, I am replacing X with a copy of M of X vertices like that, a clique, and then it will be connected to all the original neighbors of X, that is all of them will be, right. multiple expansion will happen like that. Now, for instance, when you put one more, then both of them are connected to all the neighbors, and two, all of them forming a clique, and all of them are connected to the original neighbors, and so on.
So
right?
all are connected to X.
All
Will be connected.
all will be connected to each other, not only X. Every day, expansion happens one after the other, no? Right? So it will be connected because now X dash is a neighbor of X, so it will be connected to X dash also, right?
Are we removing X after
No, no, no. See, we won't remove, for instance, depending on what is the value of m of x. If m of x is equal to 0, you have to remove. That means if a particular x did not appear in any of these sets, you have to remove it. If it appears in exactly one such set, then you just keep it as such, you don't disturb it. If it appeared in two of them, then you make the twin, right? If you saw it in in three of them, then what do? You have total 3 copies of that, including the original, right? 3 copies. And remember, all these twins will form a clique among themselves, and they are all connected to the original. So, including the original set of neighbors and this copies, mx copies, they are all forming a clique now, right? Okay, we made a graph G dash like this. It's a huge graph probably. It can be a huge graph, right? Now, we are going to, okay, observe that because G was perfect, now this new graph G dash, which is created by expanding the vertices of that, is also perfect, right? No doubt about it. So, we have G dash, which is a perfect graph. Therefore, for G dash, the chromatic number has to be equal to the clique number. So, we will try to compare the clique number of G dash and clique number of G dash and the chromatic number of G dash. And we will show that it is going to be different, and therefore, it will be a contradiction, right? And the contradiction comes from the fact that for every ki, I could find an Si which is not intersecting with it. So, at least one ki should be there which is intersecting with all independent sets, and therefore, originally some trivial argument would have allowed us to this thing. This is the plan, right? But now, how do we do this thing? For doing this thing, we should know what is the clique number of this G dash. I have to get a formula for the clique number of G dash. Okay, tell me how will I get the clique number of G dash? That's not very difficult. How is this cliques formed in G dash? Big cliques are formed. How? Maximum? He says when I expand the maximum clique is what we get the clique number. Is it so? Not necessarily, because each vertex is expanded in different multiplicities. So, it is coming from some clique, not necessarily the maximum clique, but it depends on the multiplicities. So, if you take one clique, say say K, and it had the vertices U1, U2, U3, say UT, then this clique will convert to what? This clique will convert to a big clique in K dash, which will be M of U1 plus M of U2 plus M of UT. Do you agree with me? That is the way the cliques are formed, right? So, it is always coming from some clique, because right, because otherwise it should, like if some vertices are, the twins will anyway form small cliques only, but if they together should form a clique, the original thing should have been a clique now. Because if something was not forming an edge between them, the corresponding blocks of cliques will not have edge between them. So, try to imagine this thing, this is very important. Not very difficult to see, but just imagine how the cliques or the big graph is formed from the cliques of the smaller graph. It can only come from cliques of the smaller graph, because each vertex is replaced by an m of x copies of that, but they are forming a clique. Some small balls are representing each vertex now, collections. But then between two balls, if there is any edge, that's because originally there was an edge. So if together there is forming a clique, that means original thing, when you project it back to the original, there should be a clique, right? So it's only coming from arising from the original cliques, right? And how big it is essentially this sum, right? If the original clique was this, it will become the sums, because each vertex was replaced by so many. Okay, please let me know if any of you did not get it. It's simple enough. Questions? So we are telling how big cliques are formed in. We don't know what exactly is the where exactly which clique is converting to the biggest clique is not very clear, but there is some, right? So some clique, maybe this some, that's why. So maybe this k, this is the biggest clique. So we have to write that for each u element of k, so m of u. This is the cardinality of the biggest clique in G dash. But then how big is this? We don't know, right? That's the biggest clique. Yeah, every vertex in the graph is expanded. Yeah. And now let's leave the estimation of this thing. But let me ask, what will happen to an independent set in the G dash compared to the independent set in G? The cliques are increasing, we saw that by this summing up the multiplicities. But what will happen to an independent set in G dash compared to the independent set, biggest independent set in G? Will it increase? No. Do you agree that it cannot increase? Why? Because whichever independent set you say, take, right? So from this, if a u got multiplied into m of u of things, only one of them can take part, right? You cannot take even two among them because they are anyway adjacent to each other, right? So one of them can take part from each this thing. So take that independent set, you can project it back to the original, because you need just one representative, right? That should be there, right? So therefore independent set size hasn't increased, right? It may decrease in some sense sometimes. Why? Because sometimes you may have a multiplicity of 0. So you might have thrown away some vertices. So it might have reduced. So this is what is happening. Alpha of G dash is less than equal to alpha of G. So now I want to talk about the chromatic number of G dash. Chromatic number of G dash can be at least lower bounded if we know alpha, right? See, actually chromatic number of G dash will be greater than equal to n of G dash, the number of vertices in G dash, maybe you can say G dash, divided by alpha of G dash, which is greater than equal to G dash divided by alpha of G. Because this is smaller value, this is, even if you put a bigger value here, it will only become smaller, right? So, but how much is this? How much is that? You need to know what is the upper thing. See, not that all these things here is alpha sized, alpha sized, right? Now, can anybody tell me what is the exact value of G dash? G dash means the number of vertices in the constructed graph. What is the exact value of that? It is the sum of the multiplicities of all vertices. Actually, this G dash is equal to the sum of all vertices, its multiplicities. But what is the sum of these multiplicities over all the things? So, it is kind of some kind of in algorithm analysis and all, you see individually you do not know information, but together you can get some information, some kind of an amortized arguments, right. So, when I sum over all vertices, I can get an exact number for this thing. Can anybody, the clever guys can tell this? So, you look at it and tell me what is sum of m of u's. If I add up all the multiplicities, what will you get? Once again? Alpha, they are saying this is equal to alpha into n, right? Sorry, alpha into h, alpha into h. Why is it alpha into h? Can you talk a little louder, slightly? Each one is alpha. So, see, they are saying that if you add up the multiplicities of all the vertices, it is equal to adding the cardinalities of all these SIs. Why is it so? Can anybody tell me why exactly it is so? It's correct. Why? It's you might have seen in combinatorics, one important technique is double counting, right? Double counting means, so usually we use combinatorics, some of the simple techniques, but with difficult to use, like pigeonhole principle, difficult to come up with. I mean, like clever arguments are difficult, but another such thing is double counting. So you count the same thing from this way, that way, different ways. Double counting. Double counting does not mean that the same thing is counted twice, but the same set is counted in two different ways, two different perspectives, and equate it, right, and get some information. This is one such thing. So, summing up it in M of U, the M of U's is one way of counting the cardinality of the number of vertices of G dash. Another way is to look from the perspective of these guys, right. So, you can ask inside each SI and ask each vertex of an SI. So, have you contributed to an increase in the number of vertices of G dash? It will be contributed when that particular vertex came and asked yes or no, right? Okay, that he might have told yes, I am here, right? Okay, but how many times that one vertex inside a particular SI will tell yes? Only once, because a particular vertex, that vertex should come now and ask, are you there inside it? I will say yes. But once, he may have copies in another thing, but from that particular SI, he will only come tell one yes. So, one vertex inside each of them will say only one yes, and they will say one yes. Right? When that particular vertex comes and asks, are you there? He will have to say yes. And for no other vertex, he can say yes. Right? And therefore, it is exactly counted once. And each of them give alpha. So, total number of times yes is told is alpha times h. And for each yes, we have put a extra vertex there, right? Which extra now we have put a vertex. So, this is actually alpha h. It's important to understand this thing. So, if you put alpha h here divided by alpha is equal to h. So, this happens to be, so your chi of this is greater than h is what? The chromatic number of your G dash is greater than equal to h, at least h. I hope all of you understood it. This is a simple, interesting double counting strategy. Actually, you might not have noticed that the number of vertices in G dash is equal to the number of yes, right? How many times you heard yes? Because every time you heard yes, somebody was making his multiplicity, right? And then that many times he copied himself. And another guy came and counted his yes. But interesting thing is, this yes was being told from a different person, right? From each SI, one guy was only telling one yes, because if he told yes to one person, he will never tell yes to another person, because he is that particular vertex, right? So then, so therefore, it's actually the total number of yes we heard from a particular SI is exactly the cardinality of that SI, and therefore the total SS is actually alpha times H, right? But this is not enough. We have to somehow get this also. So now what we have got is the chromatic number is at least H, right? If we show that now the clique number is strictly less than H, then we have got a contradiction, because G dash is a perfect graph. So chromatic number has to be equal to omega of G dash, right? If you somehow show that omega of G dash is strictly less than H, we have got a contradiction, because the chromatic number is at least H. So how do you show that this omega is strictly less than H? That means omega cannot have, the biggest clique cannot have a contribution from all of these things, or something like that. I mean, so you look at the biggest clique, some vertices are part of it. So each vertex might have asked these guys to tell yes or no, right? Can anybody complete the argument here? And a total yes, that set of vertices taking part in that clique which form the biggest clique is totally strictly less than H. It can never go above H. Okay, even tell why you tell me why it cannot go beyond H. Not H times alpha, beyond H. Why? Think about it. I mean, you have to be a little clever and observe things, right? Because these entire proofs are based on nice observations. What is the key observation we want here?
Click intersection, that's independent set is not 5 for all clicks.
Once again?
For all clicks, K1 to KH, intersection with that independent set is non-empty.
Non-empty. So,
But we assume
okay, it's a band of people, which is forming this entire big clique is formed by some miniature clique now, which became a big clique. That small set of people are coming and asking these independent sets, am I there, right? To that full set of clique, they complete, is any one of us are there, is what is being asked to a particular SI, suppose. Well, how many S will come? Only one. Why? Because from that clique, only one can be part of that independent set, not two can be part of them, because it's a clique, right? Because we are asking an independent set, a clique is coming and asking how many of us are there in you. Only one can be there. If two are there, then that's not an independent set, right? So therefore, for full clique, you will get only one yes, right? So from here you will get one yes. Maybe here also you will get one yes. So together you may get H yeses. So it cannot go beyond H. But our claim is that it won't even go to H. Why?
because one of them will be
Because there is one place where we get no. That is the assumption, no. Because when that particular clique is here, which is going, and then when he reaches here, this guy will say no, none of you are here. Because there was an independent set corresponding to that. That's how we cooked up this, right? For each clique, we put an independent set which is not intersecting with it, right? Which is not even having one intersection with it. So there you will say, see, no, none of you are here, right? That's why I am your partner, right? So not a single member of you are there. So there will be 0. So there is a place you hear 0 here. Everywhere else you will 1, 1, 1, maybe. So together it will be maximum H minus 1, maybe less, right? So this will be less than H minus 1. less than equal to h minus 1, this will be greater than equal to h. So, chromatic number is strictly greater than the clique number. So, which means that G dash is not a perfect, but G dash was created from G, which is a perfect graph, by expanding vertices. It has to be perfect, right? This is a contradiction. So, where is the contradiction coming? From this no answer, right? That is where the contradiction is coming. So, that means it is not possible for every clique to have an independent set such that it is not cutting it at all, not intersecting it at all. That means there exists some clique which intersects every maximum independent set. In the complement, it means there exists an independent set which intersects all maximum cliques. That means when I remove that independent set, all maximum cliques will reduce its cardinality by 1. That means the maximum clique cardinality will go down by 1. So, we can color, because it is an proper induced subgraph of complement, you can apply induction hypothesis and know that it is perfect graph. So, it is an omega dash minus 1 coloring is there. One color extra for this independent set. That is it. So, this is the proof. I do not know how many of you followed it. This is a little more trickier than the earlier proofs. If you did not follow, you just take the video and watch. Okay, that's a nice proof. So, if you 2-3 times, if you hear, you will understand. So, how many of you claim that you have understood? Nobody. Then I will go. 3-4 people have understood. Okay, fine. So, this is 1 o'clock. So, any questions on this thing? We have a little time. So, maybe you need not get into another proof here. Any question on this thing? Any clarification required? Any part to be repeated? You can ask. What is the part which is most difficult in this thing? Who is confident here that you can repeat this proof? Right now? Anybody? No, there should be some brilliant ones who has understood and definitely this is a little tricky, the proof, the entire idea, but then in the afternoon, I think what you can do is probably rerun the proof, because ask several portions of the proof and try to reproduce the proof. We can make a sequence of questions and then